On the 8th of April 1945, soldiers from an American infantry regiment broke through the perimeter of an aircraft manufacturing facility concealed at the edge of a forested region in central Germany. 3 days of fighting had preceded the breach. 3 days of working through prepared defensive positions, losing men to ambushes in the tree lines, advancing by meters rather than kilometers against a defense that had every reason to hold, because the people defending it knew what was inside. When the soldiers entered the production floor, they stopped. On the concrete stood 4 aircraft unlike anything any of them had seen. No tail, no conventional fuselage, no recognizable separation between the body of the aircraft and its wings. Each machine was a single, continuous shape, a vast, swept, blade-like form in which everything was wing, the cockpit buried in the center of the structure, the engines embedded within the wing itself, the entire assembly presenting a profile so flat and so unlike any aircraft in their experience that several soldiers initially failed to identify them as aircraft at all. The closest natural analogy was a manta ray, the wide, smooth, predatory triangle of a cartilaginous fish built for efficient movement through a medium that offered resistance at every point. These were not prototypes in the sense of being early or crude. They were sophisticated machines, the product of more than a decade of development, and they represented a technology that was not merely ahead of what their enemies had been doing, it was ahead of what their allies had been doing as well, ahead of what anyone else anywhere in the world had achieved. The soldiers who had fought through 3 days of German resistance to stand on that factory floor were looking at the first jet-powered flying wing aircraft ever built. And they were looking at the direct ancestor of the most advanced stealth bomber that would exist more than half a century later. The military response to the discovery was immediate. A specialized intelligence unit, working under a classified program whose name referred to a common office supply, arrived within days. The program's purpose was explicit and entirely unsentimental: acquire the most valuable German military technology before Soviet forces, advancing rapidly from the east, could reach it. The unit examined all 4 aircraft, identified the most complete example, and arranged for its transport to the United States. The remaining 3 were destroyed on site. Separately, a pair of large wing sections discovered in storage approximately 100 miles from the factory were recovered and shipped along with the primary aircraft. America had obtained a trophy that would shape thinking about aircraft design for the next generation. But to understand what made that aircraft so remarkable, why its discovery produced the specific quality of alarm that it generated in the intelligence community, and why its influence extended through decades of subsequent development to aircraft that were still flying at the turn of the 21st century, you have to go back to where it began. Back to 2 brothers in Germany in the early 1930s, in an era when the country was formally prohibited from building military aircraft and was therefore building them under other names. The Versailles settlement that had ended the First World War imposed comprehensive restrictions on German military capability, including an explicit prohibition on military aviation. The German response to this prohibition was systematic and creative. Across the country, organizations described as sporting aviation clubs were established, offering instruction in glider flight to young people with an interest in aviation. The formal description was accurate as far as it went. These organizations did teach glider flight, but the broader purpose was transparent to anyone who examined them carefully. Germany was maintaining and developing the human capital of a future military air force in the only institutional form that the treaty restrictions permitted. In these clubs, 2 brothers began their careers in aviation. The older was the designer, possessed of a visual and mathematical imagination that his contemporaries recognized as genuinely unusual. The kind of engineer who perceives the form of a solution before he has worked through the calculations that would justify it, and who then works through those calculations because he is also rigorous enough to require that his intuitions be verified. The younger was the test pilot, with the specific quality of physical courage that experimental aviation requires, the willingness to climb into a machine that has never flown and find out whether the designer's calculations were correct. The central idea that the older brother had fixed on by the mid-1930s was simple to state and remarkably difficult to execute. A conventional aircraft, any conventional aircraft, from the earliest biplanes through the most advanced designs of the period, consisted of three primary structural elements: a fuselage that carried the crew, the fuel, and the payload, wings that generated lift, and tail surfaces that provided stability and control. The fuselage and the tail surfaces were aerodynamically necessary in the sense that they performed essential functions, but they were also aerodynamically expensive. They generated drag. They required structure and weight. They increased the total frontal area of the aircraft, and therefore the resistance the engines had to overcome to maintain speed. The wing was the only component that earned its keep in the pure aerodynamic sense, the only component that contributed more to performance than it subtracted through drag and weight. Everything else was overhead. The designer's insight was that the overhead might be eliminable
if the fuselage and tail surfaces could be removed. If the crew, the engines, the fuel, and the weapons could all be contained within a wing-shaped structure large enough to hold them, the aerodynamic penalty of conventional aircraft architecture would disappear. An aircraft without a fuselage and without a tail would be dramatically more efficient than any conventional design. Given the same engines, it would fly faster. Given the same fuel, it would fly farther. Given the same target performance, it would be lighter and cheaper to build. The concept was not original to the designer. The fundamental idea of a flying wing aircraft had been described and even briefly attempted by various engineers going back to the earliest years of aviation. But his approach to realizing it was original, and the specific aerodynamic form he developed to make it work was a genuine innovation that specialists would still be analyzing and citing decades after the aircraft that demonstrated it had been destroyed. The critical engineering challenge of any flying wing design is stability. A conventional aircraft is stable because the tail surfaces, mounted at a distance from the wing on the fuselage, create restoring moments when the aircraft pitches or yaws away from its intended attitude. Remove the tail, and this restoring mechanism disappears. The aircraft that worked perfectly in level flight becomes uncontrollable the moment any disturbance introduces a deviation from equilibrium. Previous attempts at flying wing designs had addressed this problem by using control surfaces at the wingtips in place of conventional tail controls, a technically reasonable approach that worked imperfectly and created its own complications. The designer's solution was different in character. He developed a wing planform in which the lift distribution across the span, the way lift varied from the center line to the wingtips, was shaped to provide inherent pitch stability without any external stabilizing surface. The technical description of this lift distribution involves a bell-shaped curve rather than the elliptical distribution that conventional wing theory identifies as optimal for minimum drag. The bell-shaped distribution creates a specific pattern of local aerodynamic forces along the span that, when summed across the entire wing, produces a stable pitch moment without requiring a separate horizontal tail. The aircraft tends to return to its design attitude when disturbed, not because an external surface is providing a restoring force, but because the wing's own lift distribution produces that restoring force internally. The same wing geometry that provided pitch stability also reduced the tip vortices that conventional wings generate and that represent wasted energy.
Smaller tip vortices meant less induced drag, which meant better aerodynamic efficiency across the entire speed range. The bell-shaped distribution was not merely a stability solution, it was simultaneously a drag reduction innovation, and the combination of the two benefits in a single geometric feature reflected the quality of understanding that the designer brought to his problem. Throughout the 1930s, the brothers built a series of experimental gliders, each more refined than the previous, each accumulating data that informed the next iteration. They were doing what serious experimental programs always do, identifying the gap between theory and practice, modifying the design to close the gap, flying again to measure progress. By the time the Second World War began and the conditions of the designer's work changed fundamentally, the pair had accumulated more practical experience with flying wing aerodynamics than any other aviation organization in the world.
Germany entered the war in 1939 with what appeared to be overwhelming air superiority, and for the first 3 years of European operations, that superiority largely held. But by 1943, the strategic situation in the air over Germany had reversed in a way that German military planners had not adequately anticipated. The Allied bombing campaign had reached the scale and the operational sophistication required to cause systematic destruction of German industrial capacity. Hundreds of heavy bombers, protected by increasingly capable escort fighters, attacked by day. Smaller numbers of specialized aircraft attacked by night. The German air defense system, built around piston-engine interceptors and anti-aircraft artillery, was being overwhelmed by the sheer scale and persistence of the effort. The response that the German Air Force commander demanded of his aviation industry was framed as 3 numbers: 1,000 kilograms of bombs, delivered over a range of 1,000 kilometers at a speed of 1,000 kilometers per hour. The specification sounds clean and symmetric, but the engineering reality it described was something close to contradictory. 1,000 kilometers per hour in 1943 was achievable only with jet engines. Jet engines of the period consumed fuel at rates that made a range of 1,000 kilometers, carrying a meaningful weapons load, essentially impossible with conventional aircraft architecture. The fuel required to fly that far at jet speeds would have weighted the aircraft beyond any practical flight envelope. The designer recognized immediately that the specification was not contradictory given his wing geometry. The aerodynamic efficiency of a tailless flying wing was dramatically greater than that of a conventional aircraft. The absence of fuselage drag and tail drag reduced the total resistance so substantially that a jet-powered flying wing could achieve range figures that a conventional jet aircraft of the same engine rating could not approach. The range requirement, which looked like an impossible constraint for everyone else who examined it, was actually a specification that the flying wing concept was uniquely positioned to meet. The brothers submitted their proposal and received a contract that included funding for multiple prototypes and an expectation of rapid results. The financial terms were substantial for an organization that had been operating on limited resources within the constraints of a hobby club cover, and the timeline was aggressive. Germany needed this aircraft as quickly as it could be built, because the bombing was continuing every day, and every day that an effective counter did not exist was another day of industrial destruction. The physical design that emerged from this contract was unlike anything that had flown before. Viewed from above, the aircraft resembled a large bird with swept wings and no body. The wing planform traced a gentle curve from tip to tip, roughly 16.5 meters across, with the fuselage entirely absent and the cockpit recessed into the center section of the wing. The pilot sat in a space that was barely tall enough to accommodate a seated human being wearing a flight helmet, surrounded by the leading edge of the wing ahead and the trailing edge behind, with nothing conventional about the geometry of the space because there was nothing conventional about the aircraft that contained it.
The wing was constructed from materials that the exigencies of wartime resource scarcity had forced on the designers, but that turned out to have a secondary property that nobody had anticipated. German industry, in 1943 and 1944, was facing systematic shortages of the aluminium alloys that conventional aircraft construction required. Allied bombing had disrupted the supply chains for primary aluminium and for the finished structural sections that aircraft factories needed. The designers, unable to build the metal structure they would have preferred, used plywood, sheets of laminated wood bonded with adhesives and formed into the aerodynamic shapes the design required. The plywood was treated with carbon-rich compounds to improve its durability and weather resistance. Decades after the war, when researchers with access to the surviving aircraft examined its structure using analytical methods that had not existed in 1944, they discovered that the carbon-impregnated plywood had electromagnetic properties that the designers had not known about and had certainly not designed for. The carbon content absorbed radar energy at wavelengths that the Allied radar systems of the period operated on. The aircraft that had been built from wood because metal was not available, was, by accident of material chemistry, the first aircraft in history with meaningful radar signature reduction, a primitive and unintentional stealth capability that predated the systematic development of stealth technology by 4 decades. The jet engines that powered the design were the most capable small turbojets that German aviation had available, a type that had already been used in the first operational jet fighter and that produced thrust figures adequate for the performance the specification required. 2 of them were embedded within the wing structure, their exhaust emerging from the trailing edge in a configuration that distributed the propulsive force symmetrically and avoided the asymmetric thrust that a single engine failure would otherwise produce. The aerodynamic performance that the powered prototype demonstrated in its first flights exceeded expectations substantially. The test pilot who flew it was one of the most experienced jet pilots in German service, and his assessment of the aircraft's handling qualities was positive in ways that surprised even the designers. The flying wing that theory predicted would be efficient was, in practice, also pleasant to fly. The response to control inputs was precise. The stability that the bell-shaped lift distribution provided in theory was confirmed in practice, and in at least one comparison flight against the best jet fighter Germany had produced, an aircraft that was itself years ahead of anything the Allies were fielding, the flying wing demonstrated maneuverability characteristics that were competitive or superior. This result was the confirmation that the brothers had been working toward since they first began thinking about flying wings in the 1930s. The theory was not merely mathematically valid, it worked in the air, on actual aircraft, under real flight conditions. The bell-shaped lift distribution that the older brother had calculated in his head before the supporting mathematics were developed was the right answer to the stability problem, and the aircraft that embodied it performed accordingly. The subsequent history of the program was determined by events that had nothing to do with aerodynamics. The test pilot who had demonstrated the aircraft's capabilities was killed when an engine failed during a later flight, and the asymmetric thrust that the second engine produced could not be corrected before the aircraft struck the ground. This was not a failure of the design. Single engine loss was a known hazard for all twin-engine aircraft, and the handling challenge it created was manageable in principle if the pilot had sufficient altitude and experience to recover. The specific circumstances of this accident left no margin for recovery. The program continued after the crash, because the senior German Air Force commander, who had seen the potential the aircraft demonstrated, chose to expand rather than cancel, ordering additional examples and transferring production to a facility better suited for scale-up. But the expanded program was racing against a timeline that was closing rapidly. The Allied advance from the west and the Soviet advance from the east were simultaneously compressing the geographic space available to German industry. Supply chains were failing. Skilled workers were being conscripted into ground combat. The factories that were supposed to produce components for the flying wing were being bombed by the aircraft that the flying wing was supposed to destroy. When the American Infantry Regiment arrived at the factory, 4 aircraft were standing on the floor in varying states of completion. None of them had flown. The most advanced of the 4 was the most complete, fully assembled, its systems installed, its structure finished. It was the aircraft that the intelligence team selected for transport to the United States, and the decision to destroy the others immediately, rather than attempting to secure them for later examination, reflected the assessment that Soviet forces would reach the area within days, and that the technology was too significant to allow any example to fall into their hands. The aircraft that made the ocean crossing arrived at an American research facility in Ohio, where it was subjected to the most thorough technical examination that the available methods permitted. Engineers disassembled it systematically, measuring every component, documenting every structural detail, analyzing the materials at every point where the composition was uncertain or unexpected. The plywood skin was among the most carefully examined elements. The engineers who tested its radar absorption characteristics confirmed what the initial examination had suggested. The carbon treatment that had been applied for structural reasons produced electromagnetic absorption across a range of frequencies that corresponded to operational radar systems. The finding was documented and filed, and it entered the institutional memory of American aviation research at a moment when the implications were not yet fully understood, but would become clear over the following decades as radar and electronic warfare technology developed. The aerodynamic data from the German aircraft contributed directly to programs that were already underway at American aircraft manufacturers. One engineer who had been thinking about flying wing design since the 1930s and who had been following the German experimental work with close attention through whatever technical publications had been accessible across the war years, was already developing his own flying wing bomber design. The German data confirmed aspects of his own analysis, suggested modifications in areas where his designs differed from the German approach, and provided validation that a large flying wing aircraft was aerodynamically viable in ways that his own test program was struggling to demonstrate convincingly. The bomber that this engineer was building was large, a piston engine design with a wingspan substantially greater than the German aircraft, and it was plagued by vibration problems that the design team could not resolve. The knowledge gained from studying the German aircraft informed modifications that reduced but did not eliminate these problems, and the piston engine version was eventually superseded by a jet-powered variant that reached a more satisfactory performance level. Neither version entered production, but both contributed to the institutional understanding of large, flying wing aerodynamics that would eventually be applied at a scale that the German brothers could not have imagined. The direct lineage from the German wartime aircraft to subsequent American development was visible clearly enough that aviation historians, decades after the fact, identified the specific influence without ambiguity. The configuration of the German aircraft, the swept flying wing with no tail, the jet engines embedded within the wing structure, the cockpit buried in the center section, described a design philosophy that reappeared in recognizable form in the most advanced aircraft that American aviation would eventually produce. The aircraft that first flew in 1989 and that became the centerpiece of American strategic strike capability in the years that followed was, structurally and aerodynamically, the mature realization of what the German brothers had been working toward when they built their first gliders in the sporting clubs of the early 1930s. The sweep angles were different, the materials were different, carbon fiber composite instead of carbon-impregnated plywood, titanium instead of steel, computerized flight controls instead of manual cable systems. The scale was different. A wingspan of 52 meters, coincidentally identical to the dimension the American engineer had used for his post-war flying wing bomber, compared to 17 meters for the German original. But the fundamental design choices were the same choices. No fuselage, no tail, everything inside the wing. The lift distribution shaped to provide stability without external stabilizing surfaces. The engines buried within the structure to reduce infrared and radar signature. The overall geometry optimized for aerodynamic efficiency at the cost of every conventional structural feature that contributed drag without contributing lift. The carbon-based radar absorption that the German engineers had achieved accidentally through material substitution forced by resource scarcity was reproduced intentionally and systematically in the American aircraft, using engineered composite materials whose electromagnetic properties had been precisely calculated and verified before the aircraft was built. The accidental stealth of 1944 became the deliberate stealth of 1989, and the aircraft that resulted was so expensive and so technically demanding to build and maintain that the program produced only 21 examples, a force small enough that losing one to a rain sensor failure on a Pacific island represented a strategically significant event. The connection between the two aircraft was not coincidental or superficial. It ran through the specific aerodynamic innovations of the German designer, the bell-shaped lift distribution, the tailless configuration, the embedded engine installation, and through the electromagnetic properties of carbon materials that the German team had first demonstrated, however inadvertently, in a facility in Thuringia that American infantry would fight their way into on a spring morning in 1945. The four strange shapes standing on that factory floor were the end of one story and the beginning of another. The story they ended was Germany's, a program that had come closer than any other German aviation project to achieving something that could have affected the air war over Europe, that had demonstrated a genuinely superior aerodynamic concept in the most demanding test conditions available, and that had run out of time with its potential still mostly unrealized. The story they began was longer and more consequential, a story that ran through decades of American research and development, through the institutional memory of engineers who had studied the German aircraft and incorporated what they learned into their own work, through the eventual realization of flying wing technology at the scale and with the materials that the concept had always required. The brothers who began their careers building gliders in clubs that were officially about sport and actually about something else entirely had been right about the flying wing. The aerodynamic logic they had worked out, the mathematical framework the older brother had developed, the lift distribution that the younger brother had demonstrated by flying machines that looked unlike any other aircraft. All of it had been correct. They had simply been right in the wrong country at the wrong time, with access to resources that were inadequate to realize the full potential of what they understood, racing against a timeline that the course of the war had already determined. The aircraft on the factory floor in April 1945 was the best that could be done under those conditions. The aircraft that would ultimately demonstrate what the concept could achieve waited another 44 years to fly. Built by engineers who may or may not have known that the path they were following had been cleared, partially and incompletely, by two brothers with a glider and a conviction that the right shape for an aircraft was no shape at all. Just a wing, continuous from edge to edge, carrying everything it needed within itself, and leaving nothing behind it in the air except the invisible signature of its passage.